This is lecture 26 on intuition on the inverse function theorem. And perhaps I should say inverse mapping theorem, because that's really what I have in mind here. But anyway, given a function from Rn to Rn, we can ask if there exists a local inverse for f at x naught and Rn. And just like in pre-calculus algebraically, this asks the question, can we solve f of x equals to y for x equals to some stuff in y, which we'll then identify as being the inverse function of y, assuming that we can solve for it in a single valued fashion. So just to get us started, here's an example. So here's a function from R2 to R2. xy maps to 3 plus e to the x minus y plus comma 3 e to the x plus e to the y. So I like to declare variables for the range versus the domain. I've got x, y in the domain. I'm going to say a, b in the range. In other words, I'm setting this equal to a comma b just to give it a name. And so then in this case, my quote-unquote x is xy, and my y is actually a comma b. Like I'm not using the same notation here as I am in my example 1, right? So I'm going to try to take a equal to this and b equal to that and solve for x and y. So I'm trying to solve for the domain variables in terms of the range variables. And I can do that by like some relatively simple algebra. I add the equations, the e to the y's cancel, and I get 3 plus 4e to the x, and then I can solve by taking the log of both sides, and I get natural log of 1/4 this. And likewise, I can take this and plug it into e to the x. I get 3/4, b is equal to 3/4 a plus b minus 3 plus e to the y, and then I can solve that for e to the y, and then I take the log and I get this. And of course, if we have log of stuff divided by 4, that's the same as log of stuff minus log 4 by properties of log. So there you go. There's the formula for the inverse function. And, well, here's an interesting thought. Because this function is invertible, and the domain of the inverse is the range of the function, I can actually tell you what the range of the function is by looking at the domain of the inverse. And the domain of the inverse, well, that's the a and b such that a plus b minus 3 is positive, and b minus 3a plus 9 is positive. And so I can visualize that, as this is the feasibility region where both of these inequalities are met. And so that actually is also the range as it happens for this function. The domain, on the other hand, is all real values. So it's kind of neat. If you had asked me, can you find a function which takes, well, I guess it doesn't have to be everything in here. I'm not sure if it hits the edges or what, but it's something like that. It's kind of neat. It takes the whole plane and it just squishes it into that sector there. All right. So it's not hard to see that, if I had something more complicated like x cubed plus y squared plus y cubed, something like this, I wouldn't be able to isolate the y from the y cubed from the y squared. There's any number of formulas you could deal with where you couldn't hack the algebra, right? But you'd still like to know if a local inverse, at least in principle, exists. Maybe, maybe that thing we did with Newton's method will generalize here in some sense. And in fact, it does. So the starting point for that, of course, was to do what? Replace the problem of solving f of x equals to y near x naught for solving the linearization based at x naught equal to y. So the linearization based at x naught is this. If I set that equal to y, I can solve for x, right? By isolating the term with x. And then if the Jacobian is invertible, right, it's an n by n matrix, so its inverse might exist. If it does, then I can multiply by the inverse and isolate x minus x naught and then add x naught to the other side. And there you go. That's like an approximation to the inverse right there. Well, it's the zeroth. If it's the first approximate, or perhaps I think it's the first approximation. The 0th approximation is just say the inverse is a constant. But anyway, more on that in just a second. And so it seems like the determinant of the Jacobian matrix non-zero might allow us to find local inverses near enough to x naught. And in fact, that's the case. On pages 181 to 185, Edwards' Advanced Calculus of Several Variables shows that the contraction mapping theorem extends to functions on Rm, and that the argument we gave for n equals 1 local inverse via Newton's method motivated sequence, recursive sequence, likewise extends. But there are some technical details that are pretty involved. It would take me a couple hours to really go through the details there. But anyway, the result of that is the inverse mapping theorem. And so the inverse mapping theorem, as it's stated in Edwards, it's a little bit better theorem than you find in a lot of books, because it not only gives you the existence of the local inverse, it describes how you can construct it using a sequence of maps. All right, and it tells you how far that sequence of maps is away from the truth in terms of a... Oh, actually, this doesn't have the bound here. I think there might be a bound somewhere else. Well, anyway. So here it is. There's no bound actually here. All right, so I shouldn't overstate it. Maybe there's only a bound in the Newton's method, actually, now I think about it, for the error. Expressing the bound for the other theorems would be more complicated. But anyway, so here it is. This is theorem 3.3 in Edwards, and so you have a function from Rn to Rn, continuously differentiable, in neighborhood of W of a point A, then with matrix Jacobian, Jacobian of f at A non-singular, that means the determinant's non-zero, then f is locally invertible. So there exist neighborhoods U of A and V of B, and a one-to-one continuously differentiable mapping G from V to W, such that G of f of x is equal to x and f of g of y is equal to y. And in particular, this G is the limit of sequence of successive approximations defined by these equations down right here, which of course are motivated by what I just showed you in terms of solving for the inverse, right? So that's, I don't know, that's pretty, I was pretty excited about this when I first worked through it with some students about a decade ago. Anyway. So we can, in summary, what that theorem says in a nutshell is if the Jacobian of the matrix is invertible, then the local inverse exists. All right. Again, given that the given that the function is differentiable, continuously differentiable near the point. I think that's assumed. Although I'm not sure. He says C1. I think his C1 assumed continuity of the derivative. So I'm not being super careful about like what's the weakest theorem that could be stated. So sometimes I may be stating, a more greedy version of the theorem than we need. Anyway, going back to example 1, which was this, you can calculate the Jacobian, which is that, and the determinant is 4 times e to the x plus y. Of course, this is not equal to 0 for all x and y in R2, which goes to show you that a local inverse for this function exists at each point. So that's kind of neat. And then one more example, I think. F of x, y, z equal to 1 plus x squared, 1 plus y squared, comma 3z. So to calculate the Jacobian, it's actually this diagonal matrix. The determinant of a diagonal matrix is the product of the diagonals, which in this case is 12xy. So as long as xy is non-zero, we have the existence of a local inverse. And the algebra is not too hard to do here. If I set this equal to ABC, then solving ABC for x, y, z gives me x is equal to plus or minus the square root of a minus 1, y is equal to plus or minus the square root of b minus 1, and z is 1/3 c. So no trouble with z. But x and y, if they're 0, we're going to have to face the plus and the minus solutions, right? So as long as you're away from 0, By continuity, you know you stay either positive or negative, which means you can select the plus or minus solution, get that local inverse that you want. So it makes a lot of sense. Oh, I have an example 3. So f of xy equal to x squared minus y squared comma 2xy. Jacobian's this, and the determinant is actually 4x squared plus y squared. So what this means is that this function has a local inverse at points with x or y non-zero. In other words, you can be sure the local inverse exists at every point except for the origin. And by the way, I should say, the theorem does not say that if the Jacobian is singular, then a local inverse doesn't exist. It may or may not exist. I think you could find examples either way. In my experience, it's almost always the case where the Jacobian 0, the local inverse doesn't exist. But I think that's just evidence of my lack of imagination, not that it's a necessity of math. So anyway, that's it for this one. Next up is lecture 27, which is going to be a lightning review of the linear algebra of eigenvectors.